we are finally to our good friend Michael Faraday. I'm going to start out actually in the middle of the page of your notes. And I'm going to give you what he discovered, that an induced EMF is caused by, and proportional to the rate of change of the flux linkage. So remember, the flux linkage is just N times phi. Since N is constant, we can rewrite this as the EMF induced is equal to negative N times delta phi all over delta t. Now that negative sign is incredibly important. It deals with Lenz's law. We're not going to get to it in this video. We'll talk about it next time. Now, before I jump over and do some practice problems here, I would like to go to the top of your page and show you that if we move a magnet to the left here, we're going to be increasing the magnetic flux linkage in the coil and induce an EMF, as well as a current. Holding it steady, nothing is changing. This is the second one here. There will be no EMF inducement. If we pull the magnet in the opposite direction, we will see a EMF and current induced in the opposite direction to the very first time. And that is very similar to this PhET simulation here. If you guys go to phet.colorado.edu, right on the board here for you to see, and you go to the Faraday's Electromagnetic Lab Java simulation, make sure you have Java installed on your laptop. You can play around with this and check it out. I've turned the magnetic field strength to all the way up here, as well as the increase the loop area to the maximum and increase the number of loops. I did that so that my frame rate that's recording here, hopefully it will, your video will actually see that when I move towards the magnet with, towards the coil with this magnet, hopefully you see the little arrow move there. I've stopped moving. The little arrow in the voltmeter, that is, I've stopped moving, no voltage is recorded, no change in the magnetic flux linkage. I move back the other direction, and we see an EMF induced in the other direction. So move towards it, we get a negative EMF, away from it, get a positive EMF based on the orientation of the magnet and the voltmeter, So, that's it, That's pretty much Faraday's law right there. What we see is that in order to change the magnetic flux, we can do many different things. Remember, flux is phi, so we have a few different variables that we can change in there, We can change the magnetic field strength, we can change the area, or we can change the angle between the two. We can also change, if we're dealing with the linkage, the number of loops or coils that are there. So, there's an interesting derivation actually for this to get us back to the very first thing that we saw. If we start out with Faraday's law, we know that an EMF is induced due to a change in magnetic flux. I'm just going to drop the N right now and not going to worry about the negative sign. I just want to use this, to show you how we got to our very first equation. So if we consider this little wire moving here, when we move this wire forward, or this rail, whatever you want to call it, what we have here, this little thing right here is a delta A. We have a change in area, And the distance that this guy moved here is just going to be equal to V times delta T, what we see here, remember phi is just the same thing as we're going to have delta B times A, times cosine theta. Right now we're assuming that the angle between the normal of the area and the magnetic field length is 0, so we're just going to drop the cosine theta all over delta T. We're going to substitute in, our definition here for the area, and the way that we can solve for the area, or pardon, the delta area, the magnetic field strength stays the same, so really this equation looks like this. Excuse me, there we go. Since the magnetic field strength is the same, the only thing that's changing is the area. The delta A that we can solve for here is just going to be equal to the length times the speed times the delta T. And if we put all of that in here, sorry, this is kind of getting a little crowded around here. We put that all in here, we have B times L times V times delta T all over delta T. And hopefully you guys are seeing where we're going with this. These delta T's cancel out. We're left with the EMF is equal to B times L times V. So that's connecting it all the way to before we were dealing with a straight line conductor moving in a magnetic field. We derive that using our right-hand rule and our definition for magnetic force and applying a force balance. And here we've shown it using Faraday's law. It's really cool when you can come about these things in two different ways. All right. So let's do a few example problems of Faraday's law. There they are. A coil of wire, all right, area equal to 0.030 meters squared with 300 turns of wire. That means big N's with 300, right? It rotates through that magnetic field in a time 0.10 seconds. All right, the magnetic field has an intensity of 0.25 Tesla. What is the induced EMF? So remember here, the EMF is going to be equal to negative, right, N times delta phi all over delta T. So remember that phi, any of these variables can change, all right? What we're dealing with here, we're going to keep everything constant except for one variable. The only variable that is going to be changing here is theta, okay? So we'll be looking at this as the change in theta in the end. Keeping everything else constant, all right? Negative N times B times A, okay, is equal to, times, all right, cos theta 1, theta final, which is 60 degrees, minus theta 1, which is 0, right, all over delta t, which is 0.10 seconds. So I'm actually going to substitute all those numbers in right now, since I don't have much space. All right. Let's see if we can fit this in here. 300 turns times 0.25 Tesla times 0.030 meters squared. Oh, that's written so small, I'm so sorry, but you know what the numbers are. Okay, actually, you know, I'm just going to keep this as variables because I can't read that. So negative N, B, A, you can substitute those on your own, and when you put all that together, you get 11 volts. Okay? The next question, all right, asks us what is the induced EMF if the coil was stationary at 0? Okay, but the field strength is what changed. So when we rewrite this whole thing, it looks like the following, all right? And what's actually going to end up changing here is the field strength. So we can keep all the rest of it outside. That's just me rearranging it. And what we end up with when we substitute our values is 32 volts. Please substitute your own values as everyone else space here, okay? All right. You can check that work as well, make sure I did it correctly. Yeah. And actually, sorry, that should be negative 32 volts. So what is this negative sign? Well, we're going to talk about it a little bit. But let's just talk about the EMF. There's some graphs here, okay? Solve a few more examples before we get to Lenz's law, all right? So for the first one here, we have a 50-turn coil of wire, right? It has an area of 0.20 meters. We should be able to solve for, all right, the EMF induced in the coil during each of these little time intervals. So what we have, each of these time intervals, all right away if you look at the graph, the delta t's for all of them are 2 seconds. And the only thing that's changing here, since the number of turns is constant, the area is constant, it's the B that is changing, okay? When we solve for that, all right, we have N times the area times cosine of theta. And theta, by the way, in this situation is equal to 0 degrees. All right, times delta B all over delta T. All right. What we end up with here, the first region, since delta B in this region is equal to negative 0.060 Tesla, all right, we end up with solving for the EMF as being 3 volts. Part 2, there is no change at all, so the EMF is equal to 0 volts. And in part 3, the EMF is equal to negative 1.5 volts. okay? When we draw this out here, phi, all right, is, since everything is related to a couple of constants and b, it's going to change in the same way that b changes over that time interval. It should look something like that. All right, the EMF, which we just saw for here, the graph would look something like this, 0 and then half that value, negative, right? And then the current will follow that, whatever it is, times the resistance, or divided by the resistance for the EMF, okay? Oops. So those are just the general shapes of the graphs that they ask you to sketch, okay? For each time-varying flux that we have there, we're asked to graph the EMF, all right? If we do this, all right, remember, EMF is equal to negative n times delta phi all over delta t. Delta phi all over delta t, what does that look like to you? Well, if you look at these graphs, like the phi times t graph, that's just the slope, all right? And it's negative that. So if we have a negative slope here, the EMF that we're going to be producing until this time is going to be positive. And it switches over until this time, at which point that whole time it's negative, okay? Switches back over here, so come up, it's positive again, back over here where it is negative. So that's all that's happening there, and it's constant. The slope is constant. However, here in the second graph, we have the slope, okay, that is not constant. This is the slope, this thing that we want to note here. For those people who are curious, the EMF, all right, is equal to basically just the negative time derivative of the flux. So looking at this graph here, we have a cosine curve. Excuse me, a sine curve. Take that back, I'm sorry. So it should be a negative cosine curve that we get when we draw this here. So just make sure I get everything drawn the way I should. Comes up through there, go to the next one up there, come back down through here, next one through here. So next one there, through 0 here. There we go. It should look something like that. Okay? All right, that should do it for Faraday's law.